Now, we will continue with our discussion of alcohols. And so we're in the second video now. We'll look at the preparation of alcohols via reduction. And there's going to be a number of different methods here. Then we're going to look briefly at the preparation of diols, and then the preparation of alcohols via Grignard reagents. After this, we'll go on to look at the reactions of alcohol. So up here, we're still going to be in the preparation of alcohols. So, remember, we have already discussed as methods to prepare alcohols the reaction of alkyl halides and the additions to alkenes. And so now we're going to look at a third method, and that's going to be the reduction of a carbonyl. So you know what a carbonyl is. It's a carbon-oxygen double bond, and we've discussed this. The reduction of a carbonyl is basically replacing one of the carbon-oxygen bonds with a carbon-hydrogen bond. And that's going to be a reduction. So what do we mean by reduction? We can look at formal charges, and we can look at oxidation states. And so you may remember that to look at formal charges, you regard each of the bond as covalent and break it homolytically, and you can see that the carbon is left with 4 electrons. That's the formal charge. This is the way that you would calculate what's the formal charge on an atom. And here we look, and then you would compare this versus its place in the periodic table. Here, oxidation state, you treat all bonds as ionic and break them heterolytically. So you have to consider which one is greater in electronegativity. And so carbon is greater in electronegativity than hydrogen. So the carbon-hydrogen bond is treated as if both of the electrons are residing on carbon. Then oxygen is higher in electronegativity, and so you treat it as if both of the electrons in that bond are residing on oxygen. Now, so the oxidation states for carbon, this is totally separate from formal charges, remember. So it can range from methane, where carbon is bonded to 4 atoms, which are all lower in electronegativity, or all the way up to 4 bonds to oxygen, which of course is higher in electronegativity. And so it can range from -4 to +4. And when you go to greater and greater number of bonds to oxygen, of course, that's an oxidation, and this is what you would expect. If you increase the number of bonds to hydrogen, this is a reduction. And so going in this direction, carbon's oxidation state is increased. Going in the opposite direction, carbon's oxygen state is decreased. Now, converting a carbonyl to an alcohol requires a reducing agent because you're adding hydrogen across the double bond. And the reducing agent is oxidized while the carbonyl is reduced. And so the addition of H2 across the double bond, as I said. So let's look at the first one. The first one, as you might expect, catalytic hydrogenation. That's one of the most common reducing agents, and it's one that you've probably seen a lot. It does work, but it's not used so much because high temperature and pressure is required, and there are, just other easier and safer ways to accomplish this. One of those is sodium borohydride. Now, this is a cheap and safe reactant, and so you simply mix this. It's done in the liquid phase. You mix this with your carbonyl, and you can do this. You can actually run the reduction in the presence of the neutralizing compound. So the ethanol, methanol, or water can be in the presence of sodium borohydride because the sodium borohydride does not react with these. Sodium borohydride is a mild reducing reagent, and it gives high yields. So you'll need to remember that, sodium borohydride. It's very common. It's a source of hydride, as you can see, and you simply regard this as a source of H minus. The H minus does an attack on the carbonyl. The pair of electrons moves up to reside on oxygen. In this molecule, you consider boron as a metal. And whenever you have a metal hydrogen bond, the reaction occurs by the pair of electrons in the metal hydrogen bond does the attack on whatever it is that it's reacting with. In this case, it's the carbon of the carbonyl. Now you have an alkoxide, which then removes a proton from water or whatever workup agent you have. And in this case, this is a one-pot reaction because the sodium borohydride does not react with water. So then you have, this is your target molecule. You have now generated your alcohol. If you have an unsymmetrical ketone is reduced, a new chiral center is created, and so you have both enantiomers in equal amounts. So you do not generate any optical activity in this sort of a reaction, as always. You know, this is sort of a planar face here. The oxygen, carbon, carbon, carbon all lie in one plane, and so with equal probability, the hydride can come in from either side of the molecule. Lithium aluminum hydride. This reagent is more reactive, and it will accomplish the same reaction. Notice this is a two-pot reaction, and so first you would add the LAH, that's the abbreviation for lithium aluminum hydride. You would let it proceed to completion, and then after that reaction has completed, you would add the water later. It is not one pot like the sodium borohydride. The mechanism is very, very similar. It's analogous. And so here you would simply have H minus attack at the carbon. The pair of electrons moves up onto oxygen, exactly as you saw on the previous transparency. Let me go back and see if I missed anything. So they're comparable. Borohydride, aluminum hydride. Remember, aluminum is exactly below boron in the periodic table. So you would expect them to be very much alike. Now you can see H minus attacking, a pair of electrons moves up. Now you have your alkoxide. And then after this reaction has run to completion, then you add your water. Here the alkoxide plucks a proton off of water, and you've generated the product plus hydroxide. Now you can see here's the catalytic hydrogenation. Notice that not only does it react with the carbonyl, but it also reacts with the double bond. However, the sodium borohydride hits only the carbonyl, as does the LAH, to give you the cycloalkenol. So here you have the double bond preserved, and there it is reacted. Both of these are in excellent yields. 90% yield is a great yield. The reactivity of the hydride delivery agents can be changed a little bit. It can be tweaked by changing the alkyl groups and that's been studied a lot. So the R could be an alkoxide, it could be cyano, it could be sterically hindered groups. This has been studied greatly in the literature. Lithium aluminum hydride is also strong enough to react with carboxylic acids and esters, and it will give the alcohol that way. And so what happens is this group departs. This group departs. The oxygen that's left is the carbonyl oxygen. In each case, notice that you have to use excess lithium aluminum hydride because you are you're putting two hydrogens on this carbon that originally had no hydrogens attached. And in both cases, you're going to generate only primary alcohols. You can't make a secondary or a tertiary alcohol from this. You'll only have one alkyl group on the carbon. Now, reduction of an ester requires two equivalents of hydride. So here you can see attack at the carbonyl carbon using H-. The pair of electrons moves out onto oxygen, then the carbonyl pi bond is reformed, and so the pair of electrons is pushed back, reforming the carbon-oxygen pi bond. And remember, carbon can only bear 4 bonds, and even though it's not a very good leaving group, the best leaving group on here will be methoxide, and so that's what departs. Then once it departs, you have the carbonyl reformed. It is reformed in this step, and now this can react again with aluminum hydride, and the pair of electrons attacks here at the carbonyl, so hydride attacks here at the carbon of the carbonyl. The pair of electrons in the pi bond moves out onto oxygen. Once again, you have an alkoxide generated, and it plucks a proton off of water. So once again, you will have this reaction take place, and then water will have to be added to affect this workup step. So methoxide is not a good leaving group, but here there's no other leaving group, and this is a very high energy reaction, and so that takes place. Lithium aluminum hydride is a very reactive reducing agent. Notice it does not, lithium aluminum hydride does not stop at the aldehyde. So this tells you that if you have an aldehyde and you treat it with lithium aluminum hydride, you will generate the alcohol because this goes through the aldehyde. Now let's look at diols. So this is propane diol. So notice you have 3 carbons, and so the name comes from propane, the parent alkane, and then diol. This is a 1,3 propane diol. This is a 1, 2, 3, 4, 5 hexane diol. Notice that it's numbered in a way such that the hydroxyl group, the first occurring hydroxyl group has the lowest possible number. So this will be 1, 2, 3, 4, 5, 6 instead of 1, 2. So sometimes this is called glycol. It's the word glycol does refer to alkane diols. So this is ethylene glycol. Diols can obviously be prepared from the reduction of diketones, and so by any of the 3 methods that we just discussed, you can convert this dione into a diol. Remember that we have already had 2 syntheses of diols. One is from the per acids, such as MCPBA, metachloroperbenzoic acid, followed by acidic dilute acid, and that gives you the anti-diol, or you can use osmium tetroxide or potassium permanganate to give you syn addition and the cis diol. We had that already in the chapter on alkenes, so there it is for review, just to remind you. Now, another exceedingly valuable preparation of alcohols is the Grignard reagent, and this is going to have multiple steps in it, and it is an exceedingly important reaction, and so I strongly recommend that you do learn this. You'll almost certainly see it again because it's a very important reaction. So the first step, you go back to the alkyl halides, which we're very familiar with now, and you use magnesium. This is just magnesium metal. It's what's called magnesium turnings, so it will be not really necessarily grains of magnesium, but larger grains of magnesium, I guess. So it's just simply a magnesium metal. These magnesium turnings are dropped into the liquid alkyl halide and stirred, and you can see the turnings gradually dissolve, and you will obtain the Grignard reagent. Now, what's going on here, the way you would draw this mechanism, is you would draw a pair of electrons on magnesium, and you have a pair of electrons in this carbon-halogen bond. And so you would draw this as a pair of electrons. This pair of electrons would attack magnesium, and the pair of electrons from magnesium would then attack X. And so you're breaking one bond and forming two new bonds. Both of those bonds are to magnesium, and this is just discussed in terms, you would say, that magnesium inserts into the carbon-halogen bond. And this can be done with chlorine, bromine, iodine. It's a very, very common reaction. And Grignard reagents are very reactive also. And this can be done at an sp3 hybridized carbon or an sp2 hybridized carbon. And also the stereochemistry of the alkyl group is retained. And so here you can see it inserted into an sp2 carbon bromine bond or an sp3 chlorine bond. More on Grignard reagents. So you would draw this as a partially negative charge on carbon and a partially positive charge on magnesium. You can think of it this way, although you probably don't really have this counter ion just floating around like this. It's probably associated. In other words, the carbon-magnesium bond has some ionic character and some covalent character still left to it. So, but this behaves as a carbon anion, even when it's drawn like this, and it would be better to draw it like this. And so then when it reacts, you would start your arrow here at this carbon-magnesium bond and draw it to depict the nucleophilic attack that way. This is a strong nucleophile and also a strong base. You usually want it to behave as a nucleophile and not as a base, because if this behaves as a base, it's just going to pluck off a proton and give you benzene. And that's not a very inexpensive way to synthesize benzene. So you wouldn't want to waste this by using it as a base. You want to avoid using it as a base. You want to use it as a nucleophile because it's sort of expensive. So Grignard reagents react like LAH, and they're strong nucleophiles, just like LAH is a strong nucleophile. So here, the Grignard reagent functions by providing R minus, although it's not going to be a free R minus like what is depicted here. So you would use the pair of electrons to attack at the carbon of the carbonyl. The pair of electrons, the pi electrons, move out onto oxygen, giving you the alkoxide. And so here, the R does not have to be the same as these others. These could be like methyl, and this could be phenol, whatever. So you can add a different alkyl group in this way to get your tri-substituted alcohol. And so you here notice that the workup step, the addition of the water, is a second step. You would not put your water in here because the Grignard would react with the water like a shot. And so you'll have the nucleophilic attack done, you'll have the alkoxide formed, and then you add the water as a workup to protonate the alkoxide. So what is different here from all the other syntheses that we've seen is that you form a new carbon-carbon bond. Now remember, I said to you earlier, much earlier, probably last chapter, that you have very few ways of forming carbon-carbon bonds, and I would point them out to you. You're only going to have 4 in this course, and you've had only one other one before, and that is when an alkynyl anion attacks an alkyl halide. So here is your second one. This is the Grignard reaction, where the Grignard reagent reacts with a carbonyl. This is your second way of forming a new carbon-carbon bond, and every time you form a new carbon-carbon bond, you are increasing the carbon skeleton. So that's why this is a very important reaction. So, as I said, you don't want to have your Grignard in the presence of water. It will react like a shot to give you the alkane, which is not going to be very synthetically useful. So you try to avoid water coming into contact with the Grignard reaction. And so, you wouldn't use something like an alcohol or water as a solvent. You will use some aprotic solvent as the solvent in your Grignard reaction, which this is not. So here are examples of a Grignard reaction. So here you would get this methyl magnesium bromide, which is your Grignard reagent here, and you will attach methyl to the carbonyl carbon and then protonate the oxygen. So it's essentially adding methyl and hydrogen across the carbonyl. Here, once again, you're adding methyl and hydrogen across the carbonyl. Notice this is racemic because this is a ketone, this is an aldehyde. But since that is an sp2 hybridized carbon, these 4 atoms or these 4 atoms or these 4 atoms are all going to lie in a plane. And so when the methyl comes in, it can come in from either side of the molecule, and so your product will be racemic if you have generated a new chiral center. In this case, you use to react with an ester, you use an excess of the Grignard reagent because you need to add 2 equivalents of the Grignard reagent because you're going to need 1. You can think of it as displacing methoxide. You're going to need 1 equivalent to displace methoxide and then a second equivalent to react with the new carbon-oxygen pi bond that is formed when the methoxide departs. Okay, So this is the end of the preparation of alcohols. And so in the next video, we will go on to the reactions of alcohols.